Good afternoon, everyone. Hope you're all enjoying the Race Summit so far. And yeah, thank you for coming to our session. We will be talking today about Mako, which is Netflix's next generation ML training platform. But before we begin, I want to start with some introducing myself. My name is Avin. I'm the engineering manager of the training platform team at Netflix. And over here with me, I have...
Hey, I'm Matan. I'm a senior software engineer here at Netflix, having worked on our training infra for about 4 years now.
Awesome. So hopefully you all have used Netflix in the past, but if you haven't, we are here to entertain the world, one fan at a time. And we do this from our reach, where we entertain over 500 million people, from our recommendations, where we help you discover something great every time, and through our fandom, where our series and films become a cultural moments. We use ML in Netflix in many different ways. These are some examples. When you go to our homepage, you see a whole bunch of rankings of contents. We use ML to power that up. We use for localization, where we use multimodal algorithms to power localization at scale. Conversational search, where you can kind of type what you kind of shows you feel like watching, and it will recommend you those contents. And personalized artwork. So these are some examples. Before we go further, I kind of want to give you a high-level overview of Netflix's ML platform. Right? This is what powers the ML under the hood. You can break this down into 4 high-level pillars. The very first one to start is our feature and data infra. Think about this as your feature store, embedding store, datasets management, and so on. Next, we have the model training and offline inference. This is where Mako resides, and over there we have the Mako platform. On top of that, we do things like offline inference, GPU optimization, Metaflow, which is a project that you might have heard of here. And there's the online inference org. They do everything related to low latency, model serving, and ML tooling team, which is all about model tooling, model registry, portals, and so on. I want to take a step back and give you guys a little story about how it all started. This goes back to Manta, V1 of our training platform. This started back in 22 as an experimental way to help simplify distributed training, where we built the first durable array cluster to support a small group of researchers scale large-scale experiments. And the adoption grew quite quickly, and we scaled our capacity multiple times, and it quickly became the backbone for many of the personalization and recommendation models powering the Netflix home experience today. On a very high level, you can see the diagram there, where we have our scheduler, where users will essentially submit a job, and that scheduler will dispatch this into multiple different clusters. Going a little bit more deeper into our V1 architecture of Manta, you have the users, and we have individual clusters for interaction, different sort of production clusters, and the scheduler would route jobs into different clusters, and at the bottom we have the high-performance storage, like FSX, that would be powering that up. The key distinct here is that it's a durable array cluster, not an ephemeral array cluster, and that has its pros and cons, and we'll talk a little bit more about that in a bit. We also saw from 22 to 24 a few different things. The models became much, much larger. We went on from going like 100 million parameter models to 100 billion parameter models. Just became a norm, right? And more teams across Netflix started training large-scale models. But not all of them could use Manta due to constraints of being it a durable array cluster. And running jobs on Manta also started overloading the head node, because there's a noisy neighbor, and over time your head node starts slowing down. We also saw 4x growth in terms of number of clusters and 3x year-over-year growth in our Manta GPU fleet. But things started breaking at scale. The Manta cluster supported the first generation of large-scale training at Netflix, but it started struggling with the later jobs. And my team, the training platform team, we were just swamped with so many operational issues. So in order to overcome all these issues, we created Mako, which is the V2 platform. And Mako, we just released in beta just a few weeks back, and I'm really excited to show you guys all a sneak peek of Mako today, because this is the very first time actually publicly we are talking about the features of Mako openly. When building Mako, we had a couple things into consideration. We wanted to make sure that Mako is more reliable. We also wanted to make sure that Mako is less opinionated and Mako is more scalable. Let's just dive into a little bit more deeper into these three segments. We wanted to make sure Mako is reliable because Mako emphasizes cluster reliability, ensuring that the user training jobs complete successfully without very minimal platform errors. And this is very important when doing large-scale distributed training. We also wanted Mako to be less opinionated. And to be honest with you, this really is a key element for Mako to be gaining this organic adoption within the company, where we provide a paid path for things to happen in Mako, but at the same time, the end users, they have a lot of flexibility in terms of how they want to change their things based on their own knowledge and ability. And also more scalable. We know that Mako needs to be scalable for future-proofing this because we know the size of the model will continue growing in the future. Now, I'm going to pass it to Matan, and he's going to talk more about the internal architecture of Mako.
Sure. Thanks. So this diagram shows two sample jobs going through Mako. The training platform provides a Mako client that researchers can use to define and submit their jobs. When users define their jobs, they specify the resources they require, for example, the number of nodes and GPU types, the commands to run on those nodes, or just on the head node if they're using Ray, as well as the runtime environment through Docker and requirements.txt. That job is submitted to the training platform scheduler, which queues it for later execution. When the jobs execute, they run on Titus, Netflix's compute orchestrator, and Mako has access. With Mako, we've set up some private GPU pools in Titus for certain high-end GPU types, for which Mako has exclusive access. In this example, in job 1, it's using a couple high-end GPUs, which are coming from the private GPU pool, and a couple CPU nodes, which can come from Titus's company-wide shared pools. When the job starts, all of the nodes are fully containerized, and Mako performs peer discovery and gang scheduling so that all the nodes, when they come up, they discover each other and can set up an array cluster that includes only the nodes running for that job. All the nodes also have access to FSX Luster for fast data loading. In the second job, in this example, the user might submit code that does not need Ray. For example, if they're running existing distributed training code with maybe PyTorch, Torch Run, or DDP, and in this example, they're also using low-end GPUs, so we can run those on Titus's shared pool. Mako still performs peer discovery and sets up the necessary metadata for other distributed communication frameworks to initialize. The jobs can communicate through Torch DDP and still have access to Luster for fast data access. Mako is built to provide a couple of key features. So the first is ephemeral clusters and containerized jobs. Ephemeral clusters meaning that the Ray cluster only persists for the duration of the job and only includes the nodes within that job. This is to remove noisy neighbor issues and work around scaling limits with the Ray head node. Containerization, we use Docker and UV for runtime management for further isolation. Mako implements gang scheduling through peer discovery, fate sharing, and coordinated submission to our compute cluster to provide multi-node jobs. And we have a custom scheduler with standard features like fair share and oversubscription to balance multi-tenant access to the compute resources. All of this is built on top of Titus, Netflix's compute orchestration layer. And by running on Titus, we're able to offload many of the lower-level infra concerns, such as node management or CUDA driver upgrades, to a central cloud infra team. A key component of Mako is the scheduler. This is a custom batch job scheduler that we built for both Manta and Mako for decoupling queue management and scheduling policies from the underlying compute cluster, with development led by my colleague Kedar. This supports most standard batch scheduling features like FIFO and priority-based scheduling, gang scheduling for multi-node jobs, fair share, and borrowing and lending to optimize cluster utilization. It also provides us with a customization point for any additional ML-specific scheduling needs that we might have. It also has this really nice UI with development led by my colleague Javier, where we can show users not just scheduling information like queue state and job state, but because it's specifically for an ML platform, we can attach ML-specific entities such as checkpoints, experiment tracking links, or performance profiling. In order to interact with Mako, the training platform provides an SDK, which we call the training toolkit, much of the work led by my colleague Vinko. This includes the Mako client through which users define and submit their jobs. Within the job, the training toolkit also provides standard utilities for common ML tasks for distributed training. So this includes like making it easier to use ray train, making it easier to use checkpointing or experiment tracking or profiling, and all of this is integrated back into the Mako DB. On the slide, there's an example submission script, as well as the training script that runs on the ray head node to launch distributed training through ray train and the training toolkit. A particularly nice feature that we recently added in the training toolkit by my colleague Michael is auto tracing. So when users run distributed training jobs through the training toolkit, we'll automatically instrument TensorFlow and PyTorch code to collect performance traces at a standard point in training. Those performance traces are then stored in our trace store and made available to researchers through the scheduler with a nice perf visualizer. This is great for the researchers since if they notice their job is slow, they already have the performance profiles ready and they don't need to spend time figuring out how to instrument their models. It's also great for us as platform engineers and our partner perf engineers since we already have a pool of performance traces to proactively identify optimization opportunities without waiting for researchers to come to us complaining about slow jobs. I'm going to switch to some of the challenges that we've had building a training platform. So one is around gang scheduling and bin packing. For some of our GPU types, we see a pretty broad range of job sizes, ranging from single or 1 or 2 GPUs to multi-node or full node large jobs. Without careful placement policies, the cluster can become fragmented, and so while we may have many individual GPUs available, there may be very few whole nodes available to run large jobs. We found 3 different ways to address this issue. The first is that when we hit a fragmented cluster, to preempt small jobs and defragment resources to free up whole nodes. This can be overly disruptive for certain workflows, and so we're not able to enable this to set this by default, especially if they don't have checkpointing or they have very infrequent checkpointing. A second option is to split our GPU pool into a small pool and a large pool, with a small pool only serving small jobs and the large pool only serving large jobs. This prevents this fragmentation issue, but it reduces cluster utilization, since if we have very few small jobs, we're not able to use that extra capacity for our large jobs. Our solution is a slight variant of this, where most of the cluster is reserved for large jobs, but a small part is available for both small and large jobs. This way we limit the fragmentation to a small portion of our pool while still having access to all of the resources in case only large jobs are coming in. A second issue with building a training platform is with training optimizations, specifically around data loading. Many of our models are quite I/O bound, and so without careful data loading optimizations, the GPUs would be running at very low utilization, waiting for the data to come in. Our solution to this is FSX for Lustre, a high-performance network file system with speeds rivaling local SSD. On some of the initial jobs that we tried this out, we achieved almost a 24x speedup due to faster data loading. We use FSX as a cache for S3. So when users have their training data in S3, there's an equivalent path in FSX where they can read that data from, and it will be automatically hydrated. To further speed this up, when a user job starts, they can tell us the directory where their training data is, and we'll preemptively hydrate the whole directory in FSX for even faster data loading. When a user job is done and the data is no longer needed, we have a cache eviction daemon, and so that we can free up our FSX cache to make room for the next job. For fast writes, we provide both fast local SSD as well as S3 fuse to speed up uploads compared to the S3 CLI. A second issue is particularly when scaling from single node to multi-node, where inter-GPU bandwidth is very high, but inter-node bandwidth by default is very low. And so often jobs, when they scale from single node to multi-node, see a very big drop in performance as their GPUs are waiting for gradient synchronization across the network. A particular place where this is painful is with large models, where we're not just parallelizing with data parallelism, but we're using other dimensions such as model and tensor parallelism, which are even more bandwidth intensive. And so without advanced networking, our model and tensor parallelism dimensions are limited to what we can fit on a single node. Our solution is AWS EFA. This is a fast network device that you can attach to EC2 instances. It provides RDMA and has similar behavior to InfiniBand. On our simple benchmarks internally, we see about 80x improvement in inter-node bandwidth when using EFA, which brings the inter-node bandwidth within a factor of 2 to 3 of intra-node bandwidth. It makes it possible to do, makes data parallel multi-node training pretty trivial, and model-intensive parallelism much more possible with careful optimization. I'm going to finish off with 2 applications that we built on Mako in addition to regular distributed trading. So the first, in collaboration with our offline inference platform team, is async inference. In this example, a user might come to us with a request to run inference that's expected to take between 5 and 10 minutes. This inference request might not be so frequent as to warrant an always-on service, so we run it as a batch job. But at the same time, since the request is so short, we're very sensitive to the overhead from running it through Mako and the job start latency. That latency is dominated by the container start time, the runtime environment creation time, and the model loading time. In order to reduce the startup time, we worked with our compute platform team to cache all commonly used Docker images on our private Mako nodes so that we're no longer pulling from a central registry. And we also set up an FSX cache for the model weights so that instead of downloading from S3 to local SSD and then into memory, we can directly read from FSX. With these 2 optimizations, we brought the overhead down from 7 minutes to 2, and we're exploring other optimizations around the image, virtual env creation to further reduce the time. A second application is our LLM post-training framework led by my colleague Bao Lin. This provides standard LLM post-training methods such as supervised fine-tuning, offline and online RL, and has all integrated with different parts of our infrastructure. Mako is key to enabling this since it's less opinionated API, better matches the more complex distributed communication patterns that we see with RL, where we're no longer running simple SPMD distributed training style workloads. Also, by not having a shared array cluster, it has much fewer constraints on the packages, Python versions, Ray versions, and CUDA versions that we're able to run. And this is key since many of these tools are under heavy development and need bleeding edge versions of their dependencies. With that, I'll hand it back to Avin to close this out.
Thank you, Matan. So what's next for us, right? Well, we want to continue adopting the latest OSS tools. We want to use OSS, and when OSS does not provide a business value, on top of that, incrementally develop on top of OSS and give back to the community. We also have a plan for Mako to go to GA sometime Q1 of next year. So hopefully we'll come back here again next year in 2026 Ray Summit and talk about our experience of taking Mako to GA. Continue scaling large-scale and jobs and clusters. We know that this is something that will continue growing as models kind of expand, and we will continue making sure we tune our infrastructure to support that. Finally, make it easier for high-level workflows to happen. We want to make sure that anyone in the company, regardless of their experience of distributed training, be able to spin up a large-scale distributed training job and perform various sort of optimization. I also want to share with you all some lessons learned along the way of having taken Mako from initial idea all the way to beta, where it is right now. The first thing is aligning with OSS, right? This OSS infrastructure is significantly more robust than it was a few years ago. So the bar for creating something completely scratch every single time is much higher. So like I was saying earlier, that we would like to keep on using OSS, and when OSS doesn't provide value on top of that, when it does happen, we incrementally build something custom based on the needs. Built for generality, we have teams doing various different things, training different types of multimodal algorithms. So we don't want to over-index in one specific approach. We want to not overfit in one specific approach, leave it up to the end users to kind of drive that experience. Finally, design for adaptability. ML methods are changing rapidly, so is the infra. So what we're building right now may not be relevant 3 years down the line. I'm sure things will change. So how do we adapt to this very rapidly changing field? Mako is designed in such a way where all those different components earlier that Matan mentioned, those things are very much replaceable. So in the future, let's say a scheduler, there's a better OSS scheduler out there, we can simply swap that without having to go through expensive migration process or having to refactor a lot of code base from scratch. It just was another principle that we kept in mind. With that, thank you so much for coming. Would love to take any questions you guys may have. Yes.
Speak a little bit more about the auto tracing that you mentioned there. It is provided by some generic library integrations within PyTorch and TensorFlow, or is it something you've custom built, etc.?
Yeah, this uses the TensorFlow and PyTorch tracers. It's just making sure that it's always on without requiring the users to know which particular profiling configs or framework from TensorFlow or PyTorch to enable.
Thank you. And sorry, the other question is the ephemeral clusters that you now spin up, right? How
Yeah.
do you persist the metrics and other things after those clusters are finished, right? Do you have the head nodes running always, or do you persist them by sending those metrics from Prometheus to some other place, etc.? Just curious about that part.
So we're able to associate our compute platform, like the task IDs, with the Mako job, and so we're able to say, like, from this Mako job, find the task IDs and find the metrics for those. There's still an open problem for us if there's like Ray-specific data that may be lost when the job spins down. Yep.
Yeah, so for all of the internal customers, so how do you trace the cost, other than relying on the tagging stuff, or you don't have to worry about that on Mako?
We do, like, we have visibility into how long each job is running and which team or org each job is associated with, so we can roll that up for cost tracking.
Can you speak about the scale of the data that your training jobs are consuming, and how long do your training jobs run? The median training job, is it days? Is it hours?
We have jobs running anywhere from, let's say, hours to a couple weeks.
And the data is like hundreds of terabytes?
It really varies. Yeah.
So how does it compare with the Ray scheduler, internal object scheduler versus this job scheduler you have as part of Manta? Because real jobs can scale on their own, have more task-based optimizations depending on the resource constraints. So how does it compare with the scheduler you have on top of it?
Yeah, so one of the things that's important for us is multi-tenancy. So if multiple users are submitting jobs, we may say that this job belongs to this queue, this job belongs to that queue, and these queues have different capacities, or you want a fair share between the queues. All of that is not really possible to express to the Ray scheduler. The Ray scheduler is just about finding the right node, but beyond that, it's more just like first in, first out.
But it does delegate some tasks from one node to the other depending on the GPU resources available.
It's based on what's available, but if there's if there's a queue of tasks to run, we may choose on a policy that's not just FIFO. I think you had kind of.
So can you share a little bit more on your practices using FSX, especially on the scaling part? Since, from my understanding, FSX offers like a limited capability in terms of scaling, especially scaling it down. So what's your practice? Like, for example, can you just have customized code to clean it up?
Yes.
Okay.
Yeah, so we have a system, like we have a cache management system where users say, I need this directory, and then for this job, when that job is complete, we know to evict that data.
Right, but what if there is a spike for a surge in usage and then you're hitting the limit of that FSX system? Like assuming you have just one shared system across.
Yeah. Generally, our usage, while it's like spiky within day, it's not so spiky across days. So if we do see a consistent improvement, consistent increase, we can upsize our shared FSX volume to account for that.
And then just stay there.
Yeah, it doesn't scale down.
Just want to check, how does a user define the resource required by the job? Is it like a configuration of machine, or more about GPU, CPU of that resource?
Job resources are defined as a list of what we call an instance. An instance is like a node type, so like P4D, H200, whatever, and the number of GPUs. So you can have like one instance which is one GPU, that like one A100 GPU, or an instance that's 100 GPUs, and then they can specify multiple instances within a job to form an ephemeral cluster.
And so there will not be really a case where multiple jobs or tasks from different jobs will land on a single machine because I believe the way the resource are defined will consume the whole machine.
No, so it's possible to schedule a single GPU job. So if we have an 8 GPU physical machine, multiple single GPU jobs can land on the individual GPUs on that physical.
So in that case, how will the isolation work on these jobs?
Through Docker. Yeah, yeah. Our compute platform takes care of the isolation between instances on the same node. Yeah. Yep.
Thank you for the talk. How do you decide or pre-compute whether something is a smaller job or a bigger job?
For us, it's just based on is it small jobs is anything below 8 GPUs, like less than a full node.
So it's based on the resource investment.
Yeah.
Thanks for the talk. Is there any plan to open source it in the future?
No, unfortunately, it's very tied to the rest of Netflix infrastructure, and so that's been our focus, is just getting it up and running.
Can you speak a little bit about the preprocessors that might be used during model training and stuff? How do you persist them? What kind of preprocessors do you use? Again, is it framework-specific preprocessors? Or, for example, certain things might be available in PyTorch but not be available in tree-based models. How do you then persist those preprocessors to be then used at serving time, both in real time and batch intervals?
That's not something I'm super familiar with. We're mostly agnostic to like the specific code that's being used here. And so for us, the preprocessor might be like for ephemeral preprocessing within the training pipeline. So if you want to load, run some last mile transformations, and then feed that into the GPU, sometimes those transformations might be CPU intensive, and we might want to offload that. We have separate systems for maybe doing offline batch inference as that sort of preprocessing, or Spark-based data processing.
Thank you.
Yeah, what are the reasons of considering an ephemeral cluster on array instead of persisting array cluster? Why did you have ephemeral array clusters?
So two reasons. One, we found that if you run array cluster for long enough, we've hit many issues with the head node slowing down. Like job submission can take minutes in the worst case, or just like freeze up, and then we have to restart the cluster, which is a pretty bad user experience. And the second is reduced isolation. So without proper containerization, like user jobs can interfere with each other, or in some cases, certain frameworks, like certain data loading frameworks, for example, when they complete, they might leave a zombie process holding onto GPU memories, which is very, like Ray doesn't clean up that. So if you tear down everything as an ephemeral cluster, like there's no way for one job to like leave around these sorts of zombie processes or zombie files that might mess up the next job.
Do you also, sorry, I was going to ask follow up is, what's the latency involved in that? Like, if a job is submitted, then do you have to recreate a new cluster and wait for the job to be scheduled? Like, is that minimal and something can be accepted trade-off?
Yeah, so we talk a little bit about job start latency. It's a couple minutes, which for our jobs are generally an acceptable amount of time.
Sorry, just want to follow up on FSX. I'm just curious if you guys profile the use of FSX versus like I/O performance, FSX versus just EBS volumes, and have you seen like any like significant advantages of FSX over just
The nice thing about FSX for us is that we can have many different clients all reading from the same FSX, and that scales much better than EBS. So if we were to, for example, create like a new EBS volume per job, I think that performance would be pretty close, almost the same as FSX. With FSX, it's a little bit operationally easier to have a single storage volume and not really have to worry about hitting the limit, like I/O limits on just the number of clients reading from it.
Yeah, question. You mentioned you support the EFA.
Yes.
You increase the bandwidth by APX.
Yes.
Is that needed, like must use Ray to support that, or is support for both with EFA?
we don't need rate to support that. So like PyTorch, you just set certain, like certain environment variables, and it will pick up EFA. Yep.
Is there any kind of matching that happens in the scheduler when it's trying to run different jobs? Let's say some job asks for 1 GPU, and then you make that for the whole instance to be used.
No, so we rely on splitting instances, so we're able to schedule just a single GPU at a time. We don't proactively batch.
Do you have like a case where the number of jobs are more than the number of instances available?
Like the number of jobs to schedule is more than the number of GPUs we have available? Yeah, so then we just queue. We have like a batch inference platform that might receive individual requests, and those might be batched. But at our level of the stack, we don't assume that separate jobs can be batched together.
So there's no like optimization to have like a full set of infrastructure that is being utilized towards different systems?
No, we just try to, we schedule all the jobs that we can. Yeah.
Is the user able to submit jobs with different priority status?
You mean, yes. So like within a queue, we might have, high priority, like these are prod jobs that need to run versus low priority. This might be like a parameter tuning job, which is like run whenever.
The back.
Here's what the complexity of changing from persistent to ephemeral, because if you use something like kuberate, isn't it a difference of like, rate cluster versus rate job? And then I'm also curious if using an ephemeral cluster, does that impact the experience of if the user is using a notebook and wants to like launch like a rate cluster?
We don't use kuberate operator right now because our infrastructure like is Titus, so Titus doesn't allow that kuberate operator out of the box. That's why we have to do a whole bunch of like pure discovery and manually hooking up the head node and worker node. That's something we are working towards, and when that happens, I think that will be a little bit more easier from the operational perspective.
And then from like a notebook's interactive perspective, is there?
Yes, a few of our users did ask us like, hey, in one hand we can like have a Jupyter notebook up and running on the head node, right, and they can SSH into it, but that's something we kind of have discouraged right now. So it's mainly a large-scale batch submission. We may open up other possibilities for more of an interactive workload later in the future.
Okay, I think
Awesome.
we're done.
Yeah, thank you. Thank you, everyone.
Thanks so much.